And thank you, Donna, for remembering to record. So this is our November Statistics and Data Science and Aging Interest Group webinar. We'd like to start out by thanking our sponsors. And here is a QR code. If you would like to donate to our group, you can go to this website. And our chair, Charlie Hall, has asked me to remind everyone that ASA Giving Day is coming up, I believe, next week. So please, if you are able, any amount of donation that goes to the ASA, you can denote our group, and it all goes to helping sponsor webinars and our activities that we have at the various conferences. So we're very grateful for our sponsors. I do want to mention our next webinar will be December 11th, also at noon Eastern Time, and we have a wonderful speaker, Angel Garcia de la Garza. He is still working on his title and abstract, so I will send out the materials hopefully later this week or early next week before Thanksgiving. But you can hold the date on your calendar. Also, I just wanted to extend a big thank you to all of our members, especially Donna, our ASA contact person, who helps a lot behind the scenes. And thank you to our executive committee. It's been, a wonderful group to work with, and we look forward to developing more programs in the future that will benefit you. So I have a few slots for next spring open for webinars. So if you're interested in giving a talk, or if you have recommendations, then please shoot me an email. My new email address is jamie.spicer@wfusm.edu. And so, and thank you, Donna has put the link in the chat for Giving Day for ASA. So at this point, I'm going to stop sharing my screen. So Liwa, you can share your screen while I introduce you.
Sounds good.
And I do also want to mention that please, if you have questions during the webinar, please use the Q&A feature, which will enable us to ask questions at the end. Okay, so Liwa Lee is an associate professor in the Department of Population Health Science and Policy and the Department of Geriatrics and Palliative Medicine at the Icahn School of Medicine at Mount Sinai. She serves as the co-director of the Population Research Methods and Measurement Core at the Claude D. Pepper Older Americans Independent Center. Recently, she has completed a fellowship with the American Statistical Association and the National Center for Health Statistics at the CDC to tackle methodological challenges in using national surveys. And today, we are very excited to have her. Liwa is also our publications officer, so we appreciate all of the work that she does for our group and putting the newsletters together. And we're excited to hear about her work today involving propensity score weighting analysis for complex survey data. Thanks, Liwa.
Thank you, Jamie, for the nice introduction. And I also really appreciate the opportunity to share my work and also get feedback from my colleagues. So today, my presentation is about some of my work, which is about propensity score weighting analysis for complex survey data. Before my presentation, I really would like to acknowledge that this work was supported by my fellowship award from American Statistical Association and the National Center for Health Statistics, CDC. First, I'm gonna start with an overview of some causal inference concept under the setting of complex survey data. then followed by propensity score weighting analysis with survival outcomes. Then I'm gonna talk about a propensity score estimation methods in last. So first of all, let's maybe review some causal inference concepts under the setting of complex survey data. So we know that propensity score is the probability of being assigned to the treated group conditional on observed factors. There are typically there are 4 ways to use the propensity score. For example, we can match on propensity score. We can also construct, based on propensity score, we can construct a different type of weight than weight for propensity score. We can also stratify based on propensity score, as well as just propensity score as a covariate. So mainly in this presentation, I'm gonna talk about a propensity score weighting analysis. So propensity score weighting method is pretty much very well established in observational studies. So the central idea of doing propensity score weighting is that we want to create a pseudo population with very similar distribution of observed characteristics. So the idea is to reduce confounding and therefore bias of the estimate. So when we perform the propensity score weighting analysis, usually there are 2 stages involved. So the first stage, we call it a propensity score estimation stage. So during this stage, we derive the propensity score by regressing the treatment or exposure status on the observed baseline covariates. And then the second stage, once the propensity score is derived, then in the second stage, we usually call it the outcome modeling stage. So in this stage, we regress the outcome on the treatment or exposure status while incorporating the propensity score based weights. Yeah. So when we perform the propensity score weighting analysis, so the main causal inference is to compare the potential outcome Y1, that is the outcome under the treatment status, and then Y0, which is the outcome under the control status across a certain population. So the estimate of interest are often average treatment effect, ATE, and then ATT, average treatment effect on the treated. So ATE is defined as the difference in the expected value of the outcome between the treated group and the control group. Then ATT is defined as the difference in the expected value of the outcome for the treated group, and then counterfactual outcome if they were not treated. So propensity score analysis, as I just mentioned, are very well adopted in observational studies. But later on, propensity score method are also increasingly applied to complex survey data in geriatrics studies to estimate causal effects. So, I give a few examples in our team or my colleague have been using propensity score method and also leveraging complex surveys. Complex population-based survey, unlike the traditional or maybe conventional observational studies, have very intricate design elements. So for example, MCBS, Medicare Current Beneficiary Survey, NHS, National Health and Aging Trends Study, those surveys, they have very intricate design elements. They have strata, clusters, and also sampling weights. At the same time, a lot of times those survey also consider oversampling as well. So sometimes they oversample a certain group of people, maybe older population, certain racial ethnic groups. And also at the same time, non-response and post stratifications are involved in designing those surveys. So those multi-level survey design is to ensure representativeness of the target population. So when we use complex population-based survey, our main interest often is to make population-level inference. So to differentiate between conventional, traditional observational study and the population level surveys, we have two sets of estimate of interest. So for example, if we use sample, then if we just specifically using sample, and then our interests are mainly sample ATT and sample ATE. But when we use complex population-based survey, our main interests are often population level ATE and the population level ATT. However, the literature regarding how to incorporate a propensity score method to complex survey data is still very scarce, I would say. So for continuous outcome in Dugoff, Ridgway, using simulation study, they used the simulation study to compare different propensity score method with various specification of weights in the survey setting. And also Dong and his colleague also conducted a case study to compare different propensity score methods. For the binary outcome, Austin extended the work, but his focus was on the use of propensity score matching. Of course, then the estimate of interest would be reporting ATT. Then later on, Chen and my team further evaluated the performance of different propensity score weighting methods in estimating population level ATT and the population level ATE under a list of scenarios. But the gap still remains. Like, what about survival outcomes? Whether, if so, at what stage should we consider to incorporate a survey design, especially in propensity score weighting analysis? So in the first project, this is the first project we looked at, applying propensity score weighting analysis to the survey data with survival outcomes. So when we talk about survival outcomes, usually the treatment effect was measured on two scales. One is on absolute scale, so which is usually measured by survival quantile effect, SQE, which is defined as the difference in survival time between the treated group and the control group at a certain level of survival function. And then another measure is the relative measure. So we call it a relative treatment effect, which is usually measured by marginal header ratio, which captures the instantaneous header of experiencing the outcome in the treated group compared to the control group. But when we apply those things into complex survey data, as I mentioned, now the interest, is to make population level inference. So accordingly, survival quantile effect here will be population level survival quantile effect. This can be estimated using the adjusted Kaplan-Meier estimator indicated below. And then population on the relative scale, then we are going to expand it to the population level marginal header ratio, which can be, which is the exponential of the regression coefficient beta t, can be determined by solving the following partial likelihood score equations. So depending on whether survey design and in which stage we are counting them, counting them for, and then we mainly consider 3 propensity score weighting analysis. So the first method is called unweighted method. So neither in the first stage, which is the propensity score estimation stage, nor the second stage, the outcome modeling stage, the survey design elements were not accounted for those in those 2 stages. The second method, we call it stage 2 weighted. So the first stage, we don't count for survey design, but the second stage, we count for survey design as well as the sampling weights. Then the third method, we call it both stage weighted. So in both stage, we count for survey design as well as sampling weight. So the following slides, I'm going to talk about very briefly about our simulation scheme. So first of all, we simulate a population. We simulate population data, which consisted of 1 million observation, 10 strata, and 20 clusters. Each cluster contains 5,000 observations. Then we generate 6 covariates. 4 of them are continuous, and 2 binary and 1 categorical. Then we simulate the probability of being surveyed and set the probability being surveyed close to 0.005. Following that, we simulate the treatment assignment and specifying the probability of being treated using a logit equation with the overall preference of treatment being set approximately equal to 35%. And then for the outcome, we simulated a time to event outcome under the control and the treatment status respectively. Then for each subject, we generate a random number from a uniform distribution, and then generate an event time from a Weibull distribution, as indicated here. Once the data generated, then we use a stratified sampling scheme to sample the subjects. So we first sampled, 5 out of 20 clusters from each of those 10 strata. Then we drew a sample of 5,000 subjects with an uneven sample size set to 150 to 50 from each cluster. Then the subject is selected with the selection probability pi x, which was previously specified. So we repeated this sampling for 1,000 times. Then accordingly, 1,000 data sets were generated. So once the sample was selected, then we consider a list of scenarios. We first consider varying true treatment effect. Then we consider, different censoring type with, varying censoring rate. After that, we consider the level of propensity score overlap as, as shown as the figure in the right panel shows. Of course, we also consider the presence of outliers as well as different non-response rate. And in the last, as the reviewer suggested, we also consider the sample size as well. So this slide shows us a visual. It pretty much provides us a visual examination of the treated, the true and estimated survival curve using those 3 methods. So the top row is the estimation from the method 1. The second one was from the method 2, and the last row was from the method 3. So the black one indicates the black solid one, and the dashed one indicates the true treatment, the true survival curve. The colored one indicates the estimation from those three methods. So the red one indicates for the method one. The green one, indicates the estimation from the method 2. The purple one correspondingly indicates the estimation from method 3. So as we see that when the true treatment effect, which was kind of indicated by PMHR, population level marginal head ratio, changed from 1 to 3, we see that the estimated survival curve and the true treatment curve were getting more separated, especially for method 1. And this one shows the mean relative bias. This figure shows mean relative bias, mean absolute bias, and the coverage probability of the absolute treatment effect and relative treatment effect from those three methods. So it is observed that as the true treatment effect size goes up, which is indicated, the label, the x-axis, here. So that we see that as the true treatment effect size goes up, the mean relative bias of PSQE decreased, although the mean absolute bias, increased as we expected. But the mean relative bias were relatively stable for all those three methods. Method 2 and 3, so which is stage 2 weighted and also both stage weighted, indicated by the green and the purple one here. So we see that both methods yield lower mean relative bias and the coverage probability here. The last panel here, closer to 95% compared to method 1. Particularly method 3, indicated as the purple one, performed the best with the lowest mean relative bias and the coverage probability closest to 95% across most scenarios here. It's not very easy to indicate, very easy to tell, but we do notice that, the purple one, the method 3 was doing the best here. This slide shows us, when we specify the censoring, the censoring as independent with a censoring rate of 20%, we still keep the treatment preference as 35%. Again, method 2, so method 2 and 3 here outperform the method 1 with lower mean relative bias of PSQE, and then coverage probability were closer to 95% compared to method 1. But unlike the previous setting with no censoring, the trade-off of the bias, the trade-off of mean relative bias and the coverage probability were observed between method 2 and 3, particularly for the absolute treatment effect measured by PSQE at a certain percentile of the survival function. I didn't include all those slides here, but I also want to mention that we varied censoring rate, changed the censoring rate by from the 10% to 30%. And we also noticed that when the censoring rate goes up and the mean relative bias of both PSQE and PMH are slightly increased, but the coverage probability of PSQE decreased, not necessarily for the PMHR. So PMHR is always relatively stable. Then we consider the dependent censoring with various censoring rate. So the pattern seems very similar as those in the previous setting with independent censoring, but with a higher value of mean relative bias, lower value of coverage probability, while not necessarily for the mean for population marginal head ratio. So method 2 tended to perform better more often for PSQE, depending on the value of PMHR, also depending on the certain percentile of survival function. So this one is the result, a simulation result by varying different levels of propensity score overlap. I didn't include the result for PSQE, but I just, for easy illustration, I included the result for PMHR. So for absolute treatment effect, not shown here, but I can briefly tell you that the three methods were very comparable with the lowest mean AB from the method 1 when there was very strong overlap in propensity score, and also when there's no treatment effect. But when the true treatment effect exists, then method 2 and 3 consistently have lower mean absolute bias, lower mean relative bias, and the coverage probability also closer to 95% compared to method 1. So for the relative treatment effect, which is shown here, so again, method 1 achieved the lowest bias while maintaining a reasonable coverage probability across all the true treatment effect values for very strong overlap. But when the overlap was weak, then method 2 and 3 consistently outperformed the method 1 again. So to summarize, I would say both weighted method outperform the unweighted method under most scenarios, especially when the true treatment effect is greater than 1. But the performance of stage 2 weighted and both stage weighted, method 2 and 3 really depends on the time point of survival function and also the censoring type as well. So the three methods performed very closely when there was no treatment effect, and particularly when the propensity score was strongly overlapped. And also to illustrate the simulation, we use a real data example. In this example, we aim to assess the impact of smoking cessation within 3 years of cancer diagnosis on overall survival among adult cancer survivors. So using NHIS data, National Health Interview Survey data spanning 2001 to 2018, linked with mortality data through December 31st, 2019. So basically, in this study, in this real data example, we classify cancer survivors into two groups. One group is that who quit smoking within 3 years of cancer diagnosis. Then the other group is the cancer survivors who continued smoking after cancer diagnosis. And the outcome is, as I mentioned, is the overall survival. So very busy slides. Yeah, I apologize. But basically here, I want to show you the baseline characteristic of this analytic sample. So before we do propensity score weighting, as we see that their baseline characteristics are very different, systematically different, indicated by the standardized mean difference. Most of them are greater than 10%. After propensity score weighting, we see that actually baseline covariate get the distribution of baseline covariate are more close. And this figure depicts the estimated Kaplan-Meier curve, survival curve between the treated and the control group. Specifically, I mean the group who quit smoking and the who quit smoking within 3 years of cancer diagnosis, and the group who continued smoking after cancer diagnosis. So the left panel is the estimation from method 1 From the left to the right, it's the estimation from method 1, 2, 3, respectively. So overall, we see that the survival probability for those for the cancer survivors who quit smoking within 3 years are higher than those ones who continued smoking. The survival, the absolute treatment effect, so which is measured by the survival time difference, as we see that were much closer from the left panel and much separated. I mean, the difference is bigger from the estimation from method 2 and 3. If we take a closer look for the estimated treatment effect, and then we see that, just taking the median survival time as an example, when Q equal to 0.5, right? And we see that the median survival time for both groups were estimated 39 versus 37 years, with a difference from 2 years from method 1, 3 years from method 2 and 3. If we focus on relative treatment effect measured by population level marginal hazard ratio, we see that 3 different methods give the estimate 1.18, 1.19, and 1.18 respectively. So very close. Basically, we can conclude that smoking cessation, even in 3 years of a cancer diagnosis, was associated with about a 20% decrease of mortality risk. So followed that, we did a second project. So we know that a propensity score can be derived by different methods. So a few studies already kind of compared the performance of different propensity score estimation methods in non-survey setting. But in the survey setting, the question still remains: what is the best propensity score method? Propensity score estimation method. So in this study, we aim to examine the performance of 6 propensity score estimation methods in the propensity score weighting analysis using survey data with a skewed continuous outcome. So first of all, we considered those 6 propensity score estimation method. They include logistic regression, covariate balancing propensity score, CART, random forest, generalized boosted model, and the superlearner. So still following the previous simulation scheme, we changed the outcome. Here, we changed the outcome from the survival to skewed continuous outcome. So this outcome was generated using a gamma distribution by specifying the shape and the scale parameters. And we consider varying treatment effect as well as the complexity of the model by varying degree of nonlinearity and non-additivity. Then we also varying degrees of propensity score overlap. So for example, here, when we look at the model nonlinearity and the non-additivity, we consider the 6 models. So model A, scenario A, is the model where there's no linearity and no additivity. Then we vary it until scenario G, and which is the model with moderate nonlinearity and moderate non-additivity. So the first slide, this one shows us the simulation result by varying true treatment effect. So we see that so the first 3 columns shows the estimate from the scenario under the scenario with low treatment effect. The middle one was under the scenario with medium treatment effect. We specify those values, very close to the real data example, which I'm gonna show you later. And then we see that random forest consistently yield the lower mean relative bias, lower root mean square error, and close coverage probability closer to 95%. Then it was followed by GBM competing with CART in trade-off between the bias and the coverage probability. GBM seems obtained slightly lower mean relative bias, but lower coverage probability as well. As the treatment effect size goes up from low to high, the mean relative bias from all the 6 methods decreased. So we see that when under the low treatment effect, the mean relative bias was ranged between 0.86 to 0.92 roughly. But when under the scenario with high treatment effect, the mean relative bias reduced to 0.07, something like that. The performance of all the 6 methods were less separated. The mean relative bias from all those 6 methods were very, very close, especially for those 4 machine learning methods. But when we increase the model complexity by adding nonlinearity and non-additivity, we notice that actually the mean relative bias and root mean square error from all the 6 methods increased. And especially, for the model G, with moderate nonlinearity and moderate non-additivity. And we do notice that bias definitely increased. However, the mean relative bias and the root mean square error of beta t for the random forest were again consistently lower than those obtained by the rest of the models. It was followed by GBM, CART, and superlearner when there was mild nonlinearity, which is the model B, or under the scenario with non-additivity, any non-additivity, so which is scenario D, E, and F. The coverage probability obtained from those 4 methods, those 4 machine learning methods were consistently above 90%, regardless of the degree of model complexity. But the coverage probability reaching 95% really varied among random forest, sometimes CART, and the GBM as well, depending on the scenario. So for example, scenario C, we see that coverage probability obtained by GBM was doing the best. And the last slide is showing the simulation result when we vary different level of propensity score. So as the level of overlap changed from strong to weak, so strong is the right 3 columns to weak, the left 3 first columns. So the mean relative bias changed from 0.3 about 0.14 to 0.2 to 3, yeah. So consistently, this change was consistent for all the 6 methods, while the coverage probability decreased specifically for 2 parametric methods, logistic regression and the CVPS, but not necessarily for 4 machine learning algorithms. But when there was a strong overlap, which was indicated by those right 3 columns, the 6th method yielded a very similar mean relative bias and the root mean square error, as well as the coverage probability. As the overlap level decreased, random forest again outperformed the other models in terms of all those 3 performance metrics. This is more evident when there was very weak overlap. Coverage probability obtained for machine learning methods consistently remain above 90% across all those scenarios, all 3 scenarios. So to illustrate this simulation, we also considered we also, sorry, I think, I forgot to summarize. So here, basically I want to say that when performing the propensity score weighting analysis using complex survey data to estimate a population level treatment effect, machine learning algorithm, especially random forest, appears to be a very attractive approach for estimating propensity scores. And to illustrate this simulation result, we also considered a real data example. So in this real data example, we specifically aim to assess if hospice use is associated with lower total health care cost in the end of life. Hospice use, is an indicator is indicator of a good health care in the end of life. Approximately half of the Medicare decedents received hospice care prior to their death. And recently, we have done a study, found that hospice use by community dwelling Medicare beneficiaries is associated with significantly lower total health care costs in the last 3 days to last 3 months of their life. But a potential limitation of our study is that we only utilize the CBPS to estimate decedents' likelihood of receiving hospice care, didn't conduct sensitivity analysis to assess the robustness of our finding if we use, other propensity score estimation method. So in this real data example, we still using the same data, which is from the Medicare current beneficiary survey of 2002 and 2019. And we separate those participants into 2 groups. One group is that who used the hospice, and then the other group is who never used the hospice. And we also consider the sensitivity analysis by increasing the hospice use length. So for example, we consider the group who used the hospice for at least 15 days and compare it to the no use group. And then we use those 6 methods to derive the propensity score. And then that's the first stage. In the second stage, we applied a GLM model with a gamma distribution, and then also incorporate propensity score estimated from the first stage, while also considering the survey design as well. So again, this slide is showing the baseline covariate for the analytical cohort. So unlike the experimental setting, so the groups under the observational study are always very different. So in our case, we compare to those one who never used the hospice. The group who used hospice tend to be older, more likely to be female, and also more likely to be white. They also tend to have a higher preference of having dementia and cancer, and also higher preference of higher proportion of them needing ADL help. But after applying propensity score weighting, we see that 2 groups are getting much more closer. This figure depicts the estimated association between any hospice use and the total health care cost in the last months of life. So all the 6 methods provides a very close estimate of beta, which was around negative 0.26. Indicating about $4,000 reduction in total health care costs in the last month of life. And we also noticed that the propensity score from 2 groups, from the group with any hospice use and the group with no hospice use are strongly overlapped. So this confirms that the previous simulation results, when there was very strong overlap, all the 6 methods performed very, very similarly. And we also found even larger reduction in the in the total health care cost in the last 12 months of life, comparing those one who stayed at hospice longer, so specifically greater than 15 days, compared to those who never stayed in the hospice. So we noticed that the difference in the value of estimated beta T decreased as the estimated effect size got increased. So this again may suggest that as the previous simulation setting, as the treatment effect goes bigger, then the performance of all the 6 methods improved, especially for those 2 parametric methods, logistic regression and the coverage covariate balancing propensity score. So looking forward, we are thinking of a few things, still working on it. First of all, we are thinking of expand our work to heterogeneous treatment effects, because heterogeneity in the real life is very common. For example, people's patient reaction to a certain drug could vary, could vary a lot. And for certain treatment, palliative care patients, certain treatment in palliative care could also so different. And then accordingly, the estimate of interest will be changed from average treatment effect and the average treatment effect on the treated to population level conditional average treatment effect, conditional average treatment effect on the treated. But at the same time, when we apply it, we also want to incorporate a complex survey design as well. And the last, we're also thinking previously. Previously we specified the sampling scheme was independent on the treatment or exposure status, but I think later on we are thinking, the sampling scheme could depend on the treatment or exposure status. Not necessarily here, the treatment or exposure status could be survey design variable. So for example, could be race, ethnicity, could be region, something like that. Yeah, thank you. That's all. Really appreciate the great opportunity. And now I would like to have your comments and questions.
All right, thank you, Lewa. Very interesting work. So please put questions in the Q&A, or if you want to press the raise hand button, then I can allow you to turn on your video and speak if you'd like to ask a question. But there was one question from an anonymous attendee who says, do studies of data sets such as HRS always require weighting methods?
Sorry, can you say it again, Jamie?
Okay, sure. Do studies using data sets such as HRS always require weighting methods?
Yeah, that's what I think that's what we also would like to suggest as well. Yeah, because I think when we use complex survey data, our main interest is to make a population level inference.
Yeah, so along those lines, I don't really use survey data very much, and I wonder if you could share what your experience has been like obtaining the real data sets, like getting approval. Has that been smooth? Or like any advice about like what data sets are available that people in our group might think about using in their work?
Yeah, sure. I would say actually a lot of survey data, complex survey data are publicly available. So for example, um, National Health Interview Survey, NHIS, right? People are commonly using it. And also NHANES as well, which are also publicly available. But Medicare Current Beneficiary Survey and also HRS and NHANES as well. I think those survey, I believe, are not publicly available. You usually have to either purchase it or just submitting proposals and go through the process to acquire it. Yeah.
Yeah.
Mm.
Yeah, awesome suggestions. Yeah, as soon as you said NHANES, Michelle Chardell also wrote that in the chat. So that was funny timing. Great minds think alike.
Yeah, and
Um,
also another thing that I really would like to share that, for the NHIS, and also I think some other survey as well, they are linked to National Death Index data. So basically, you can have a survey and also you follow it. I mean, for the vital status, once you linked to those mortality data, and then you have time to event outcome. Yeah.
yeah. And Heather Allure added, NHATS and HRS are in the NIA linkage, which also allows free linkage to CMS data.
Mm-hmm.
So
Yes, yes,
cool.
yeah.
Lots
That
of great resources. So there's a couple other questions that have come in. One is, what do you recommend when the weights change yearly or longitudinally?
I think it depends on the question. I would say that, if you are performing longitudinal analysis, yes, then I would say longitudinal weights should be recommended. Yeah.
Mhm.
But if it's cross-sectional, then, for example, MCBS, right? If it's cross-sectional, then ever enrolled survey weight was kind of recommended. Yeah.
Okay, another question is, were there any general patterns for when method 3 appreciably outperformed method 2?
That's really a good question. And I also saw that uh, another person asked a similar question. Yeah. Do you have any recommendation on when apply the method 2 or 3? Uh, uh, I think really I would say, yeah, we found that actually when the sampling scheme is independent on the treatment or exposure status, then method 2 and 3 really does not differ much. But I think Dugov and also Ridgway actually, in his simulation study, he found that when sampling scheme, the selection probability is not independent on treatment or exposure status, then method 3 is recommended. Yeah. But a lot of times, because in our study, we argue that the treatment variable, which is not necessarily is the survey design variable, we assume it's independent. And then we found that method 2 and 3 on the binary outcome and also, the survival outcome, they don't differ much. Yeah, there's a very slight difference there. Mhm.
Yeah, I think it's also tricky because, in data simulation studies, we can control everything, right? So we know exactly what assumptions are correct. But
Mhm.
in real data, it's often you have to just kind of guess. So do you have any kind of recommendations for how you can decide like which of the
Yeah.
scenarios would fit your data potentially?
Yeah, okay. I think that's also a great question. So for example, I would say if we specifically when we analyze those national survey, we kind of know that the survey design variables already, which is probably specified in their kind of methodology guide or something like that. So for example, when they design those survey, right? So usually age is kind of considered, and then sex as well, and also race, ethnicity. Sometimes, the states is also kind of states usually is considered as a strata, something like that. But I mean, those design variables are usually specified in the methodology guide. If your treatment is one of those variables, we do see it, and we do see some study looking at, especially race, ethnicity, and also gender as well, as the exposure variable, not necessarily treatment variable. Then in this case, yes, because your treatment variable or exposure variable is related with the sampling scheme, right? Then I would say in this case, method 3 is what I would say is recommended. And then if your treatment variable, for example, in our case, is the smoking cessation, right? Smoking cessation is not a design variable when they design the NHIS. So I would say in this case, we didn't see much difference between method 2 and 3.
Great. So I think we got all the questions that were written in. So again, Liwa, thank you so much. Your work is awesome. So keep it up, and thank you for presenting. And I do just want to mention, I had a typo in my slide earlier. The next webinar is December 11th at 1 p.m. Eastern, not at noon. It'll be at 1 p.m. So look out for that email. And yes, Liwa, again, thank you so much.
Thank you. Yeah, thank you for having me. And thank you, for your time as well.
Yeah, all right.